Our first speaker of today is Misao Sasaki, who is from the Kavli Institute for Physics and Mathematics of the Universe in Kashiwa, and from the University of Tokyo. And his topic is primordial black holes. Take it away, Misao.
Okay, thank you very much. Today I'm going to talk on this a couple of recent topics I'm working on in some sense, and on about the primordial black holes. I'm not exactly sure if everybody knows what primordial black holes are, but so first I will just briefly review this sort of a standard picture of how the black holes are formed and its relation to the gravitational waves, which has become quite a hot topic in these days. Okay, so this is the cosmic space-time diagram, which I guess everybody sort of know. The horizontal axis is the log of scale factor, which is called the number of e-folds. And the vertical axis is just the length scale, log of length scale. And in the straight line is just the constant co-moving scale. For example, in the case of the current horizon scale, and if you have this line, and which goes back to the very early universe and crosses the Hubble horizon during inflation. So you have during inflation, you have approximately constant Hubble horizon size. And at the end of inflation, you have something, we don't really know what happens in this area, but then we think that sometime later, the universe becomes radiation dominated until about a couple of 100,000 years from the Big Bang, and which is the equal time of in terms of the number of e-folds. It's about 10 number of e-folds before, from today. Anyway, but what we actually know, or all these sort of observations, let's say the CMB observations and all these things, from those that we can sort of constrain in what was essentially the initial power spectrum of the perturbations during the inflation, but which extends only, including all these some error bars, but still includes extends only maybe a 2 or 3 orders magnitude, and so this means that the among the long probably duration of inflation, we only know a few number of e-folds. So this is the current status, but this actually means that we have a lots of chance of seeing maybe new physics, or maybe discussing new physics beyond this or small scales, let's say beyond these scales which are observed by current CMB or maybe large scale structure formation and so on and so forth. Okay. Now, so one of the it's an interesting possibility is that if those have a power spectrum, which is very strongly constrained on the very large scale, have some peak on a very, very small scale. And if peak is large enough, of maybe a 0.1 or 0.01, something, which is not, sorry? Anybody has any question? No.
Oh, no.
By the way, so if anybody has any question, just maybe scream. I don't know. The Richard would probably allow anybody you to just make questions, I guess, right?
That's your call, Misao, but I would ask everybody who's not asking a question to mute their speaker.
Okay. Yeah. Oh, yes. All right. Anyway, so on small scales, you may have this kind of peak in the spectrum, and if you have that such peak, and the peak is large enough, then when it enters the Hubble horizon again during, say, radiation dominant universe, then the fluctuation amplitude may be large enough. And if it is large enough, it may form primordial black holes. So this is the most sort of standard kind of scenario that so which means that you have some, let's say during inflation, some mechanism makes a larger enhancement of the power spectrum, essentially the adiabatic perturbation power spectrum. And this power spectrum is large enough, then when the scale comes inside the horizon, essentially this whole horizon size would collapse to a black hole. So in this sense, actually, this black hole formation is not I mean, it's better understood if you consider this as kind of a formation of the closed universe in our universe. So the point is this, that while on scales much greater than horizon, you can essentially write down the sort of Friedman equation, local Friedman equation, which is essentially the Hamiltonian constraint or 0, component of Einstein equation, where you have the left-hand side, the curvature, and the curvature consists of the Hubble expansion rate squared plus the spatial curvature, and on the right-hand side, which is equal to the energy density of the universe. Now, if you just simply take the linear theory, then this curvature, three curvature, actually given in terms of so-called curvature perturbation, which I use this script RC. Excuse me. So by the way, so people usually call it this curvature perturbation. Actually, as you could see, it's the potential for the curvature perturbation. But anyway, and this is the three-dimensional curvature behaves like 1 over a square in the early universe where the scale is well outside the horizon. But of course, as a decreases, a increases, the right-hand side is 1 over 8 to the 4th, for example, in the radiation dominance, while this is 8 to the 2nd. So gradually, if the curvature is non-vanishing, curvature start to catch up. And actually, at the horizon crossing, if you just take the rough zeroth order perturbation, zeroth order approximation, if you assume the linear theory, then you have a delta over rho on the right-hand side is equal to this amplitude of the curvature perturbation at horizon crossing, and if this curvature, actually it's the free curvature itself. Oh, by the way, so at this scale, if the curvature perturbation is over the unity, then you will have this free curvature is approximately equal to the Hubble square, and this is exactly what happens to the say closed universe. In the case of closed universe, you have this curvature term which start to dominate, and the Hubble expansion becomes 0, and then your universe start to collapse. So for a universe to collapse, you actually need to have the stage where to go through the stage where the three curvatures equal to the Hubble square. Now, if this happens, then this is exactly happens at the scale of the horizon scale, then you are essentially having some sort of part of closed universe in some patch of the universe, and that can just collapse as the closed universe, which collapses in the end. So in this way, actually, you can understand how the primordial black hole is formed, at least in the radiation dominant stage. And because this is essentially a closed universe, you would expect the spins of primordial black hole to be very, very small. And actually, this has been shown recently by those people. Okay. Now, so then, given the initial power spectrum, what fraction of the those fluctuations they could turn into primordial black holes? This is computed very easily for if you assume the initial perturbations are Gaussian distributed. Excuse me. So, if the fluctuations follow the Gaussian probability distribution, then you have some distribution around the delta. Delta is some perturbation signifies perturbation. In this case, let's say delta rho over rho. If at the horizon crossing, let's say, and it distributed like this, and if the fluctuations, they may have large fluctuations, positive or negative, but if fluctuations are large enough, then probably they would just, as I said, you form some closed universe there, and your universe of that Hubble patch would collapse to form primary black hole. So this is if this is how you, so essentially you have to given this critical criterion delta C, which is probably of order of 0.4 or 0.5, and interestingly this was the value suggested by the Bernard Card in already like almost a half century ago, huh? But this number sort of fluctuate from time to time, but still it seems that this turns out to be a fairly good estimate. Anyway, if the perturbation amplitude, so for example, sorry?
Can I ask you a question?
Sure.
Hello. Yeah. So this formation of primordial black holes in the radiation dominated, is it depend on particular models of inflation, or it is more general?
Oh well,
can it happen
so of course you do need some mechanisms to form some fluctuations. So and the best sort of scenario so far we know is the inflation, because we know that the inflation produces at least fluctuation on a very large scale. So so it could also give some non-trivial large fluctuations on small scales, but that's not the only possibility, of course. So, but what I'm saying is that essentially, once you assume some kind of adiabatic perturbations on a very large scale, then I'm discussing how much of those fluctuations can become primary black holes. Yes, and this sort of approximation is very good for say this sigma square is essentially the power spectrum, or well it's essentially, well, the M means the instead of a standard sort of a variable k, the k is wave number. You can consider a some mass scale correspond to the frequency. So I mean the wave number. So this is essentially the power spectrum itself, and so if a power spectrum amplitude usually is small, because if it is order 1, actually you lose the I mean the linear perturbation theory is no longer valid, and probably universe becomes highly chaotic. But we know at least this must be smaller than 1, probably much smaller than 1. And if the sigma square is much smaller than 1, and if the delta C is order say 0.4 or 5.5, then this exponent is very, very large, which means that usually the black hole production is highly suppressed, and the suppression is exponential. But nevertheless, even if it is highly suppressed, since black holes behave like dust matter, which behaves like 1/8 cube when they once they are formed, while in the radiation dominant universe, the radiation energy density behaves like 1/8 to the 4th. So even if beta is very, very small, if they are formed in the very real universe, gradually they can catch up the energy density and becomes a dominant part. You could become dominant part of the universe. So, so actually, we have a very strong constraint on this beta, and which determines which it gives a constraint on sigma square and so on and so forth. Anyway, so currently, so assuming the primordial black holes are essentially distributed randomly in our universe, currently, and then here's this constraint. The leftmost constraint comes from black hole evaporation, meaning that if the black holes is the mass of, say, mass is like 10 to 15 grams or so, very, very small black hole, they would just evaporate by Hawking radiation today, and which would give you a very, very strong gamma ray background, which we don't see it. So because of this, we have a strong constraint. On the right-hand side, if we have a huge primordial black hole, then there would be a huge accretion onto those black holes, and they would affect CMB. It would distort the CMB Planck spectrum. And because of that, you have a strong constraint. And in between those constraints from Subaru, this is hyperspring cam. This is a huge camera. And this Eros and Macho collaboration. This uses gravitational lensing. And if the primordial black hole are distributed randomly, then they should also be present, say, in our galaxy, or maybe between our galaxy to the nearby galaxies, for example, the Andromeda galaxy. And so looking, observing all these stars in the other galaxies or within our galaxy, if we see some gravitational lensing events, then from those gravitational lensing events, we can actually detect primordial black holes. But so far, we haven't seen anything. There are some few candidates, but it's only a candidate, and we don't really know whether they are real ones. So this gives this fairly strong constraint.
Misao,
but interestingly, sorry?
I have a question. Where on this plot are the constraints coming from the non-disruption of, say, neutron stars by black holes that, you know?
Right. Yeah. So there was yes, it was somewhere here, and it was discussed that that is a possibility, but actually the assumption is that you sort of assume very high, very high density primordial black holes, and which is not so. I mean, if you assume the black holes are, let's say, the cold dark matter, then they just spread out. For example, in the case of our galaxy, like a standard sort of a cold dark matter, as you know, that it forms a halo of the galaxy. So if you just use some naively, I say how to say the standard number density and also velocity dispersion and so on and so forth, then you don't really get this strong constraints at all. And so constraint disappears in that sense. Of course, this is just there are still some debates going on, but at least the resulting constraints not robust as those, for example, constraints from gravitational lensing. So you could say that you still have a chance to have primordial black hole being dark matter. Okay, Valerie?
Okay, yes, okay.
Okay. Anyway, so interesting is that so this range, because the size of black hole becomes less than 10 to minus 5 centimeter, the spatial radius. So any optical wavelengths would be larger than the size of black hole. So this is a wave effect. Also, actually, if you look at the nearby galaxy or the nearby galaxy like Andromeda, then those stars have the size, which the finite size, this finite size effect is also very important. And because of that, you lose all the constraints. And which means actually you have a nice sort of a chance for a primordial black hole to be a cold dark matter between essentially these mass. And which, if you assume the standard sort of hot peak band up to a very high temperature, then which corresponds to the horizon scale when the temperature was like 10 to 4 or 10 to 8 GeV. That's an interesting sort of a range of energy scale as well. Okay, so but that's how you produce primordial black hole. But if, as I said, if you assume some kind of large fluctuation or large amplitude power spectrum produced during inflation, then primordial black holes are not the only one which will be produced, because those curvature perturbations, when they are large enough, you definitely form primordial black holes. This is like a closed universe, like a picture. But if the amplitude is not so large, when they enter a horizon, because it's a radiation-dominant universe, essentially they become sound waves and start oscillate. Now, these oscillations definitely have, not in some sense in the, say, Newtonian approximation, a non-trivial time derivative of the quadrupole moments or at any point of space-time. So this means that you're producing gravitational waves. And the frequency of the gravitational wave, well, if you assume those primordial black hole to be the cold dark matter, then the frequency would be about 10 to minus 3 hertz, which is essentially the gravitational, the background, the band of the LISA, the future space gravitational wave observatory. Unfortunately, it's very low, so we cannot detect this by the LIGO-WIGO sort of ongoing gravitational wave detectors. But still, in the future, you may have some very interesting. By the way, this actually means that if you increase the mass, then actually the frequency becomes higher and higher. Sorry, the other way around. Was it? Sorry, I'm a bit confused. Maybe I'm saying something incorrect. So I should come back later. I mean, soon. Oh yeah, this is good. Okay, so in this way, actually, you can test gravitational waves. Sorry, a primordial black hole scenario by gravitational waves. And as I said, well, this was actually a pioneer by these people, Saito and Yokoyama, about 15 years ago. That's and they have already, in some sense, kind of know what we can do in the by gravitational waves. But anyway, the point is that if so, the primordial black hole mass is 10 to 20 grams or so, then this can be called dark matter. As you see, this omega primordial black hole is of order 1. And in this case, this falls into this LISA band, or maybe DISIGO, or some other sort of future space gravitational wave telescope. On the other hand, if you go to a much lower frequency, which corresponds to the higher mass of the black hole, then actually you already have a very strong constraint from pulsar timing array experiments, and actually the future pulsar timing array experiment can constrain the number of the abundance of primordial black holes to be, for example, about 10 to minus 5. And actually, this is really ongoing now. And quite recently, there was an announcement by Nanograv saying that maybe they have seen some gravitational waves. If that's what, if they are correct, this means that you have some. It means that you have some primordial black hole order, maybe 10 solar mass or so, and with the abundance of like 10 to minus 5 or so. Anyway, so now we are really in an interesting situation. But so far, as I said, I focused on the adiabatic perturbations, but maybe we have some other scenarios, and recently this isocurvature, primordial isocurvature perturbation scenario becomes quite interesting, and let me just talk about this. So one of the interesting sort of cosmology is that in particle physics, astroparticle cosmology, many people consider some interesting sort of a topological object, or maybe non-topological but very stable object like cue balls and so on and so forth, which may form in the very early universe. Now, if they form in the very early universe randomly, then as you could see, I mean, this random, so their sort of a mean distribution of density of those objects will be spatially varying. But of course, those will be a very, very minor component of total energy density. So they are essentially isocurvature. Whatever the perturbation or the distribution you have, they wouldn't affect the total energy density, because energy density is totally dominated by radiation, let's say. Interesting is that in this case, actually, depending on what kind of formation scenario you consider of those objects, these fluctuations, distributions may be highly inhomogeneous, meaning that it can be nonlinear from the beginning. So far, nobody has really done any analysis of such cases. But anyway, this is a very, very interesting sort of a possibility. But of course, you cannot just have this unless you assume this to be, say, there's some cold dark matter of the universe today. We cannot have those objects to dominate our universe today. So for example, like in the case of cue balls and so on, and actually you assume that they are fairly stable, but eventually they decay and disappears into radiation. So what happens in this case is that you have the radiation dominant universe in the beginning, but this compact object eventually take over the energy density of the universe, but then decay out and become radiation again. Now, so what is interesting is that once these objects become dominant, then those inhomogeneity, some of the inhomogeneity may have been nonlinear, let's say, as I said from the beginning, mean that you may form some black hole out of those, a bunch of those, say, cue balls and so on and so forth. So this means that the isocurvature perturbation or inhomogeneous distribution of those compact formed objects can actually form black holes, depending on how many of them are formed and how they are bunched and so on and so forth. So now let me just briefly recall the how you compute this in linear theory. And so essentially, you assume the matter isocurvature perturbation. So the isocurvature perturbation usually is represented by this S, which is delta rho over rho of the matter minus 3/4 delta rho over rho of the radiation. And in the early universe, you just completely zero density perturbation, so the delta R is 0, so its approach is delta M. Now, so this R is the scale factor in units of the equal time. So when R is smaller than 1, it's radiation dominant. When 1 is greater than 1, it's matter dominant. And if you consider some modes which are super horizon at the time of equality, then essentially in the beginning, the curvature perturbation grows gradually and it becomes a constant of order S. S is the initial perturbation amplitude. And as soon as the universe becomes matter dominant, essentially the perturbation delta rho over rho also grows like a scale factor and with some of these coefficients. And at the horizon crossing, is occurs given by this condition. If you insert this in here, the density perturbation will be 2/15 times S. Now, if those criterion, I mean, we still don't know much about this, but the criterion, you can also use the same criterion for the primary black hole formation, this ice curvature case. Then this gives a criterion for the black hole formation for the initial value S. Okay, so this is fairly simple in some sense. The interesting thing occurs for those modes which enter the horizon before equality, because then it's on a very small scale, but because they are isocurvature, they do not decay, so they just stay there, and when they are when it enters radiation dominant stage, it sort of slowly grows, and it grows just continues in the matter dominant stage. Now, at the horizon crossing, if
you're right at 30 minutes now.
Oh, sorry. So anyway, okay. So the whole point is that in this case, as I said, well inside the horizon, the fluctuation can be nonlinear from the beginning, and so actually this you do have to consider some highly nonlinear evolution of those objects. The isocurvature perturbation, and this haven't been studied at all. So there's a very interesting area of which you can study. Now, I think I don't have any time to go, but you can consider the if those objects are primary black hole from the beginning, then you don't really need to form a primary black hole out of primary black holes, but those fluctuations can produce the gravitational wave, as we have seen, and we can have some constraints on various and in this case, actually, the primary black holes, we should consider primary to be evaporating, as we have considered that the Q balls must evaporate. It's same thing essentially, but the difference is that in this case, I mean, maybe it's the same for Q balls too, but some of the models. But in this case, because essentially the evaporation is so rapid, evaporation occurs not like the decaying particles, but they, in some sense, instantaneously occurs. And this instantaneous reheating of the universe from matter dominant to radiation dominance can actually enhance the gravitational wave amplitude substantially. And this is what we have analyzed. And I don't think I have much time, but anyway, you have a interesting constraints and interesting sort of a spectrum coming from those primary black hole dominated universe. So since time is up, let me just mention one small caveat. And again, this is related to the nonlinearity. I mean, so in any case, the isocurvature perturbation can be nonlinear from the beginning, and actually in this randomly distributed primary black hole case, you do have a nonlinearity already in some sense, because the amplitude of, say, perturbation of this initial spectrum S is over order 1 at the smallest scale. And so in this sense that we do need some nonlinear analysis. And here's the take-off messages that the primordial black hole may play very important, interesting roles in gravitational wave cosmology. And in particular, there are vast areas which are unexplored, which is how the primordial black hole formation due to some nonlinear or maybe linear, but the isocurvature perturbations. Okay, thank you very much.
Thank you for this fascinating talk, Misao. I'll ask people who want to ask questions to raise their hands, which you can do with the reactions button at the far right bottom of your screen. In the meantime, I think I will ask one question, and that is, could you give us an example of a model, a scalar-driven inflation model that would realize this?
Oh, yeah. Which one? I mean, the standard sort of adequate perturbation, let's say, for example. You know, I mean, so for this sort
yes,
of
that's right. I'd like to know what the potential. Suppose it was scalar-driven inflation. I'd like to know what kind
okay.
of.
So if you just assume that your inflation is just single field, let's say slow roll, then it's not so easy to sort of configure a model where you have some fairly sharp peak in small scale. But as soon as you introduce a secondary field, and if you, for example, consider, this has been studied a lot in the past, that's so-called two-stage inflation, or I don't know whether this is the proper naming or not. But so if you assume that the one field which dominates the fluctuations on the CMB scale is taken over the other field, and when you have this, which at the final, if you say 20, 30 folds of the inflation, if this happens, you can have various interesting sort of effects when you have the you kind of a change, your universe change from, say, the initial CMB inflaton to those the inflaton which can take over after the I mean the later part of the inflationary stage. So at this transition time, you may have a huge spectrum peak, for example. So in this way, you can actually configure. Well, and there are many sort of models which can actually do such jobs. So in that sense, if you just assume that everything is purely single field, then you really sort of turn the potential to a rather artificial way. But as soon as you have secondary field, then this can be avoided, and you have I don't know, hundreds of models which can do the job.
Okay, thank you. I'm noting questions from Valery Rubikov first, and then Shravan Kumar.
Yes, I understand your isochromatic perturbations you were talking about in the second part. They are initially super horizon, right? So
right.
What could be a mechanism that generates so large amplitudes for super horizon isochromatic perturbations?
Oh, yeah. Well, in the case of isochromatic perturbation, in this case, so you do need some yes, the agent, and one sort of simple thing, for example, is the some kind of what you call it, so really isocurvature field during the inflation. Yeah. So let's say you have some spectator field. Let's say those spectator field, as in the case of standards of adaptive perturbations, will be frozen. The field fluctuation will be frozen when they go outside of the Hubble horizon scale during inflation. So their fluctuations are on a large scale. So they are purely isocurvature. Okay, and they are.
But you need very large amplitudes, right?
Oh yeah. No. So sorry. Yeah. So that case you would probably, I mean, may not have very large amplitude, but it depends. For example, if you consider kind of the model like Carverton types models, then we know the fluctuations of the scalar field is of order of Hubble, right? Now so if you consider delta phi over phi, the background value of phi can be, or I mean, it maybe depends on the regions of the space, but in some space, can be of order of Hubble. In that case, fluctuation would be very, very large, right? Delta phi over phi will be very, very large. So you may have such situations. Of course, it probably, I know, in that case, you cannot really rely on linear theory from the beginning. So you have to do some highly nonlinear sort of analysis. I mean, meaning that it's really quantum field theoretical, perhaps. But still, you essentially you have such chances as well. The inflation can do that job too.
Well, that's debatable, I should say, because
Oh, yeah?
you have very large fluctuations of all scales. So your background value for Hubble seems not very sort of natural.
Oh, wait, no. So as I said, it must be isocurvature. Huh? If it is adiabatic, then it ruins everything. You see, so the energy density of such field, for example, in the case of really purely flat mass zeros, the field, I mean, that's sort of unreasonable. But in that case, you have the shift symmetry, so and the fluctuation doesn't, as apart from some very small scales, the fluctuation on super horizon scale never contribute to the energy density, right? So you may have such things, yes.
Okay, we had a question from Shravan Kumar.
Hi, Misao. Thanks for your talk.
Thank you.
I have a question regarding, suppose if the primordial black holes account for all dark matter, I mean, is it possible to account that? That's just to confirm if it is possible. Maybe I missed, you already mentioned.
Sorry. So what is the question again?
Yeah, so the primordial black holes account for all dark matter.
Yeah.
Is it possible?
So as I said, yes, this is what I said. I mean, so you do have some constraints on the very, very small mass primordial black holes and the large mass black holes, but there is this a sort of a protoplanetary object, whatever you call this, some mass around 10 to 20 gram. There's a huge sort of a open range where the primary black hole can be a dark matter. So
then my next question is, I mean, during the cosmic evolution, these primordial black holes may feed the supermassive black holes, right? At least some of them, right? Do you understand my question? I mean,
supermassive black holes. Are you considering the supermassive black hole to be created or the generated from primary black holes?
Primordial black holes. Yes,
that's on the very, very large mass, huh? Like beyond this scale, perhaps somewhere here, like a black hole mass of 10 to 40 gram or something.
Okay.
Yeah. So this is way small, like 20 order magnitude small. So they are tiny. They as I said, its size is less than 10 minus. Size is like particles or the atomic size, black hole of atomic size. So they don't contribute to those supermassive black holes at all. Yeah.
Wow.
But you can produce some seed for primary black hole. I mean, sorry, the supermassive black holes. There are some models that such models too. Yes.
Okay. Thank you.
I think our last question would be from Chen Hang Ding.
Thank you for your talk. Yeah, I would like to ask if we detect a gravitational wave from two binary black holes, their mass is around 10th of mass. So how could we say these two black holes are primordial black hole or astrophysics black hole? How could we distinguish them?
That's a very good question. There are many discussions, and of course, the simplest answer is that if we wait long so that we have all these future detectors coming out, and then and we can identify the redshift distribution of the let's say binary black hole merger, then for astrophysical black holes, you would expect that it would at least, I mean, drop off at say redshift of 10. Yes, you expect that there aren't so many, because you may form some primordial black hole binaries around that time, but it takes time to those binaries, the emit black hole gravitational wave, to merge. So you need some merging time. So this means that at high redshift of 10 or 20, you would not expect any binary black hole mergers if they are astrophysical origin. But they can happen. You will have such as high redshift binary merger sources if they are primordial. So this is the simplest answer, but you have to wait maybe a couple of decades.
Okay, thank you.
Okay, well, again, thanks, Misao, for this fascinating talk. We'll move to our next speaker.